The process of coating Parylene onto a surface provides a thin, uniform, and inert coating. The coating can be as small as 10 nanometers. It is over 99% pure, so the surface characteristics are highly predictable. And because Parylene coatings are inert, they protect the bulk material from corrosion. This is beneficial for biomedical applications because the coating does not leach chemicals into the body and it protects the device from fluids in the body. They coat elastic materials without affecting the elasticity or weight of the material. They seal microporosity. A smooth surface is harder for cells to implant on and eventually form scar tissue, which is a beneficial characteristic for implants. Because the formation of the coating occurs at room temperature, the coating is effectively stress-free or resistant to thermal stresses. It is an effective insulator or dielectric, which can be used to coat electrical components, and it also has a high tensile strength. So this shows the chemical structure of a Parylene polymer and also a few SEM spectroscopy photos of Parylene. So the first picture on the left shows a material without any coating, and then the middle one has 5 nanometers of the Parylene coating, and the one on the right has a 10 nanometer coating. And if you zoom in, you can see that the porosity significantly decreases as the coating thickens.
Parylene coatings are applied through a chemical vapor deposition process. The first step is sublimation, where powdered Parylene dimer is heated in a vaporizer to take it from a solid to a gas. The gas then gets fed into a pyrolysis furnace, where it is further heated. This additional energy separates the dimer into individual monomers. The gaseous monomer then enters a room temperature vacuum coating chamber, which contains the part to be coated. The Parylene monomers then polymerize one monomer at a time onto the part's surface, creating a growing, continuous coating. To promote adhesion of the monomers to the surface, various preparatory steps may be taken. Parts may go through a series of liquid baths containing silanes, undergo plasma treatment to increase the surface energy of the part, or just simply have their surfaces mechanically roughed to create a more favorable topography for the attachment of the Parylene monomers. Masking may also be used to prevent certain areas of the surface from being coated.
But why would we want to treat surfaces this way? Well, this allows us to create a single clear coating that is built up one molecule at a time. We can customize the thickness of this coating from less than 10 nanometers. To get a perspective of that, a piece of paper is roughly 100,000 nanometers thick, up to around 70 micron thick. 70 microns is approximately the thickness of a human hair, give or take 20 microns. Another reason why we want to use this method is because it involves green chemistry. This means that there are no cut forces, no thermal stress, no leachable ingredients onto the material being treated. Another reason to use this is because it can add properties onto the material being treated, such as making it more rugged. This also has excellent dielectric strength, meaning it has the property of transmitting electric force without conductance, and it can also improve lead-free soldering joint life on any hardware or circuits that we use it on. It is also chemically inert, which is ideal for coating any biomaterials that will be introduced into a biological system, reducing metabolic interaction. And lastly, the combination of all these previous features provide a protective barrier which repels corrosive chemicals, gases, moistures, and liquids.
As you may know, biomedical engineering can be a fairly broad field incorporating prosthetics, bioinformatics, drug development, gene editing, and tissue engineering, to name a handful. Therefore, Parylene coatings can be used in a diverse set of applications. One of the reasons that Parylene coatings are so versatile is that they provide a biocompatible protective shield for electronics. This is especially relevant for implantable devices. The body is a corrosive environment that can degrade metals through mechanisms such as oxidation, crevice corrosion, hydrogen embrittlement, galvanic corrosion, microbial corrosion, or fretting corrosion. The pacemaker, for example, is an implantable device that can keep a patient's heart beating by electrically stimulating the atrium. As you can imagine, the pacemaker has a plethora of electrical components that require significant protection from the corrosive compounds in the extracellular matrix.